Hey kids, so today we have a little bit of a lab activity today. So first thing, just do number one, two, and three. Define those things in your own words. Pause the video right now. Do that, and then I'll go through them. So current is the rate. Let's see. The rate at which charge flows. So if charge flows faster, you have more current. If more charge is flowing, you have more current. Voltage. Now, voltage is kind of the hardest one to describe. I like to think of it as the amount of potential energy, right? Or the amount of, let's say, energy. I'm going to put energy in quotes here in the circuit. Now, the reason I'm putting energy in quotes there is because it's not really energy. Remember, voltage, our analogy, voltage is like a hill. Okay, yeah, a hill can give you potential energy, but you have to have a mass on the hill to actually have the energy. Just like voltage on its own can't give you energy. But if you have a charge in a voltage, it has energy. Okay? So voltage, once you put a charge in a voltage, it has energy. And resistance, I mean, it's hard to define resistance without using the word resist in it, but resistance slows current down, right? So really important point here, this kind of sums everything up. Voltage pushes the current, and resistance slows the current down, okay? So let's check out this FET simulation for a minute. So what you're going to do is you're going to use one battery and one light bulb and some wires and light up a light bulb. Click on intro. So one battery, one light bulb, use some wires to light it up. And there we have it. Now make your picture look like the one I have there. So for example, we're going to use conventional current flow. What does that mean exactly? So back in the day, Ben Franklin kind of messed things up, and he thought that positive charges were the ones that move, but actually it's negative charges that move. But we still use his convention that he started, hundreds of years ago. So notice how the electrons are going around the circle clockwise. Conventional current is going to be opposite. Okay, conventional current is the flow of positive charges. Are positive charges actually moving? No, absolutely not. But that's just how we do things. It's the convention we use. But this isn't just in physics class. Electrical engineers use this. Electricians use this. It works, okay? There's no issue doing it. But just keep in mind that conventional current flow is the flow of positive charges, which doesn't actually happen. All right. Now, the circuit we just made is called a series circuit. We'll talk more about that in another class, series versus parallel circuits. But this is called a series circuit because there's only one path for the current to flow through. All right. Now, what we use to measure current is a thing called an ammeter. So I want you to grab the ammeter on the side, and I want you to measure the current through the light bulb, the wires, and the battery. So let's do that. Here's my ammeter. Measure the current through the light bulb, 0.9 amps through the battery, 0.9 amps and through the wires, 0.9 amps. So it's 0.9 amps everywhere. So what can you conclude about the current in a series circuit? It's the same everywhere. All right. Again, we'll talk more about series versus parallel circuits, but I figured we'd just throw this in here. So we just threw a lot of things at you. First, conventional current flow is a flow of positive charges. Okay, it's just the opposite the direction of electron flow. Maybe I'll mention that. Let's write that down. Conventional is opposite direction of electron flow. So if electrons are moving from left to right, the conventional current we're going to use is from right to left. Okay? And a series circuit is a circuit where there's just one loop. All right? The current is the same everywhere in a series circuit. We'll get more into that later. So let's graph a little. So you're going to place the ammeter anywhere in the circuit, so it's measuring the current. By clicking on the battery, you may adjust the voltage. What happens to the brightness and the current of the bulb as you increase the voltage? I think you should know this. If I increase, so let's put this here. If I increase the voltage, what do you think is going to happen to the bulb? Let's see. Increase the voltage. Well, the bulb gets a lot brighter, right? And the current gets a lot bigger as well, right? The current's going way quicker when the voltage is up and it's brighter. All right. So two things there. What happens to the brightness and current of the bulb as you increase the voltage? They both go up. Fill in the following chart by adjusting the voltage and recording the resulting current. Plot your data. Don't forget to label the increments on your x-axis. So we have voltage on the y-axis and current on the x-axis. All right, so let's fill in our chart first. So at 0 volts, what's our current? All right, so let's do that. 0 volts, 0 current. Perfect. Okay, actually I don't need to put amps there because it's already at the top of the column. Let's look at 1 volt. 0.1. Let's look at 2 volts. 0.2. And just fill it in and confirm that this trend does follow. Okay, so go through, make sure they all, keep adjusting it, and make sure that this trend is true. Let's look at 10 volts real quick. 10 volts, 1 amp. Yeah, that's right. Now, let's put in our axis. So let's think about how we can fill in our axis for current. Current goes from 0 to 1. So maybe we'll put 1 over here. We'll make this 0 0.1, 0 0.2, 0 0.4, 0 0.6, 0 0.8. I skipped every other one just to make it a little easier to see. All right. All right, so let's plot our data. So we have a 0, 0 data point, 0.1 and 1. And actually, our data is kind of perfect, and it should be because we're using a simulation. Just make sure you understand why I'm plotting these data points. Look at your data and make sure you see which one is which. Like, for example, this data point here is going to be this data point right here. All right. So hopefully you see that this is a linear relationship. Throw in our line of best fit. There we have it. So find the slope. Don't forget units. So to find the slope, a little rise over run. Let's do that in green. So I'm going to start here. There's my run. Here's my rise. Let's see, my rise is 7 volts. My run is 0.7 amps. So slope equals rise over run. 7 volts over 0.7 amps. So if you throw that in your calculator, make sure you can do that. You should get 10 volts per amp. So let's think about how we can create an equation of a line here. So our equation of a line is y equals mx plus b. Hopefully you recall that, where m is the slope, b is the y-intercept. So our y-intercept here, hopefully you see is 0, so b is 0. Which variable is on your y-axis? Looks like voltage. Therefore, y represents volts. And let's see, which variable is on your x-axis? Amps, or current. Therefore, your x is going to represent current. Where volts are V, current is I. So if you write the equation of a line here, let's substitute in y, m, x, and b. All right. So y is volts. M is, let's just write 10 volts per amp. X is current, which is I. And b is 0. So it's just V equals 10 volts per amp times I. Now the slope is the variable that relates voltage and current. Think back to the beginning of class. What did I say relates voltage and current? What's that other thing? It's resistance, right? Remember, voltage pushes the current and resistance is what holds it back. So the slope is actually the resistance. So we can conclude that the slope of the graph represents resistance. So the resistance of our light bulb is 10 volts per amp, or 10 ohms, as we know it. Now, does this agree with the actual resistance of the light bulb? You can click on the light bulb and find that out. So let's click on the light bulb. Yeah, it is. 10 ohms. So yeah, it's good. So this relationship is called Ohm's law. Okay. Now, Ohm's law on your equation sheet, so let's look at where it is on your equation sheet. On your equation sheet, Ohm's law is with the other electricity equations. It's right here. R equals V over I. Now, I personally don't like the way that's written. I much prefer it to be written as I equals V over R. You can figure that out with algebra by rearranging, but this is the way it's on your equation sheet. All right. So we'll work with Ohm's law a lot more next class. We'll keep working with circuits more and more. Circuits, like I kind of mentioned before, are an iterative topic. We're just going to keep working with them, and the more and more you work with them, the more and more everything starts to kind of pull together. But basically what I wanted you to see today, that we can relate voltage, current, and resistance using Ohm's law. Okay? Now, what you're going to submit on your Google form is a picture of this graph and chart. Basically everything for number 4. Just submit an image of it. That's it. Okay? Now what I'm going to do is I'm just going to go over the exit ticket from last class really quickly. So if you did fine with that and you get it all, you're set. So leaving a circuit on can make it get hot. How does this affect the resistance? So hotter equals higher resistance. All right? Which graph depicts the relationship between a wire's resistance and cross-section area? Hint, look at the equation. It's an inverse relationship. So let's write the equation. R equals rho L over A. So we're looking at this relationship right here. This is an inverse relationship. We don't plot an inverse relationship like this. Okay, that's a negative linear correlation. This is an inverse relationship. All right? Think about it this way. As A gets really big, R approaches 0, but R never hits 0, right? And A can't be 0. Okay? So we're going to write this equation again because we're going to need it again. So copper wire has a length. The wire is stretched. It becomes longer and thinner. Okay? This, what effect does stretching the wire have on its resistance? So it's longer, so L goes up. If L goes up, R goes up. And it's thinner, so the cross-sectional area goes down. Remember, there's an inverse relationship between A, cross-sectional area, and resistance. So if A goes down, our resistance goes up. So both of those things make the resistance go up. So resistance goes up. And last is just a math question. So during a lab experiment, a student finds a 6-meter length piece of copper, so L equals 6 meters. And it has a resistance R of 1.3 ohms. What's the cross-sectional area, A? So you also need the resistivity of copper. I could find that really quickly, just looking here. And it looks like copper is 1.72 times 10 to the negative 8. All right. So working through this, R equals rho L over A. R is 1.3. I'll leave the units out for now. Rho is 1.72 times 10 to the negative 8. L is 6. And A is our unknown, right? So we're gonna have to rearrange stuff a little bit. Let me find my calculator real quick. Cancel, I don't want to do that. Looking at my calculator, it looks like this is gonna come out to be, what is that, 7.9 times 10 to the negative 8? Meters squared. All right, so if you have any questions, feel free to ask me, but again, all you have to submit is everything inside this purple box. That's all I need from you. All right, just to take a picture of it. If you can't upload the picture to the Google form, just email it to me. All right, have a good one.